Welcome to the OpenQuake online workshops, supported by the United States Agency for International Development, USAID, as a part of the CHECK project. In this video, we demonstrate how to perform damage and loss assessment for earthquake scenarios using the OpenQuake engine. In previous videos, we learned how to estimate the distribution of ground shaking in an area affected by an earthquake rupture. We generated ground motion fields and studied the variability of ground shaking intensity using OpenQuake tools. In this video, we will discuss concepts of exposure and seismic vulnerability to estimate damage and losses using the same earthquake rupture. The session consists of a theoretical framework and a practical exercise. Within the theoretical framework, we are going to address the two components, exposure and seismic vulnerability. In the practical exercise, we will demonstrate how the input files are prepared and how the damage and loss calculations are performed. Finally, we are going to explore the output files and visualize the results through a graphical interface. By definition, risk is the result of having a spatial and temporal overlap of these three elements, a source of hazard together with exposed and vulnerable elements. Seismic risk can be described mathematically as the probability of damage or loss from potential future earthquakes. In the first part, we saw that faults are sources of seismicity and that it is possible to model a seismic event if the parameters to define the rupture of the fault are available. We learned that the ground motion models are the fundamental tool for estimating the intensity of ground shaking and its associated variability. In order to estimate damage or losses due to ground motion, we need to understand what exposure and seismic vulnerability represent and how they are modeled. We can define exposure as the man-made environment that is exposed to one or more sources of seismicity. The elements exposed can be individual assets, such as residential buildings and their inhabitants, as shown in the middle image, or schools and their students. The contents and services they provide are also considered to be exposed to the hazard, as they may be damaged and interrupted due to a seismic event. Elements that do not have a permanent occupation but have a significant heritage and cultural value for society may also be exposed. For example, religious temples such as the image on the left, or historical monuments. In the same manner, we can consider as exposure the infrastructure and networks. In this case, the exposure does not consist of one, but of several exposed assets that share a connectivity relationship with each other. These include sewage systems, the power grid, water supply system, and telecommunication networks. Another good example is the transportation network, such as the image shown on the right, where the damage to a single element, such as a bridge, can result in interruption of the entire network. Modeling the exposure consists of identifying and appropriately characterizing all the elements that are part of the risk study. This is done through descriptive attributes. As we have discussed, we can have attributes that describe the use, the contents, the economic and human value, the physical characteristics, and even the connectivity of what is exposed to the hazard. Next, we will discuss the basic attributes that are required to perform damage and loss assessment. First, we have the geographical and number attributes. It is necessary to define the number of elements and their geographical position in order to estimate their distance with respect to one or more sources of seismicity, as the ground shaking intensity is a function of this distance. As discussed previously, distance is a calculation parameter for ground motion models. We can expect elements close to the source to experience greater intensities than elements far from the source. The geographic attribute is considered essential since without this information, it is not possible to estimate the intensity of the ground shaking or the damage or loss that it may cause. Next, we have the attributes of value and occupants. To understand what the risk is, it is necessary to identify the economic value and the number of people who are exposed to the hazard. For example, if you want to perform a risk analysis for schools, it is essential to identify all the schools in the study area and how many students attend those schools, what we would call the occupancy of the assets. It is also necessary to estimate how much it would cost to repair or replace each school due to the damage. This is called the replacement value or cost, since it is the cost that the owner of the exposed asset is incurred in the event of its complete loss. The attributes of value and occupancy are considered indispensable in risk analysis, since without them it is not possible to quantify the potential for loss. Next, we have the structural attributes. It is necessary to identify the physical characteristics of the exposed elements to be able to classify them according to their fragility and seismic vulnerability. Among the main physical attributes that must be identified are the construction material, the structural system or lateral load resisting system, the height or number of stories, and the year or the design regulation. The structural attributes are considered essential since the damage or loss that an exposed element may suffer is a function of its seismic vulnerability. Let's take, for example, the two assets shown in these images. Both are single-family masonry two-story residential structures. However, the residence on the left is clay masonry, unreinforced, and not properly confined. Most likely, this house was not designed following construction regulations which would resist lateral loads imposed by earthquakes. The structure on the right, on the other hand, is made of concrete masonry, duly reinforced and confined, and it is in good condition. Its construction most likely followed construction regulations which were designed to support lateral loads. If these two structures, although similar in certain characteristics, were subjected to the same ground shaking intensity, the house on the left would present much greater damage and loss than the one on the right. The GEM taxonomy represents a classification system to characterize buildings according to the most relevant structural attributes for seismic risk assessment. In the link at the bottom, you can explore the attributes and their definitions according to this taxonomy. The way we capture the attributes required for an exposure model varies depending on the amount of items exposed and the size of the study area. At the urban or city scale level, it may be feasible to carry out detailed survey and obtain the occupation, value, location, and structural attributes from the direct inspection of each structure. The GEM Foundation has developed the IDC tool, or Inventory Data Capture tool, to carry out surveys during field inspections. It is currently available for devices using the Android and Windows operating systems. In this figure, we see an exposure model of the city of Pavia in northern Italy, made by university students using the IDC tool. An exposure model at this scale makes it possible to understand the characteristics of buildings at the most precise resolution possible. In recent years, several cities in the world released detailed databases about their built environment. In these cases, surveys may not be necessary as information regarding the exposed elements, such as buildings, hospitals, schools, and transportation infrastructure, are provided in reliable and precise databases. For example, here is a three-dimensional model of the city of Zagreb in Croatia, made using the footprints of buildings and LiDAR-type surveys, which provide information on the height, type of use, built area, and number of buildings. This information can be used to identify the exposure of the city with a high degree of detail. When information is not available at this level of detail, it is also possible to generate exposure models with other databases. For example, this is an exposure model developed for the city of Quito in Ecuador, using information about the population and the characteristics of their residences at the census tract level. This type of approximated information can be corroborated with field inspections to obtain the best results. An exposure model with this resolution allows the computation of risk metrics that can be useful to investigate the best location for disaster response centers, temporary shelters, or to identify the sectors of the city with a high vulnerability and potential for loss. When a large-scale risk analysis is required, it is impractical to determine the attributes of the exposure model at the building level. There are other tools and databases, such as national population and housing censuses, or information obtained through remote sensing, such as satellite images. These can help to determine the level of exposure at a national and subnational level. For example, here we see an exposure model for Haiti developed with census and satellite information to determine exposure at the commune level. An exposure model at this scale can be used to determine high-risk regions where it is worth investing in detailed research or risk mitigation measures at the local level. In conclusion, an exposure model can be developed at different scales depending on the scope of the expected risk assessment. In all cases, the identification, manipulation, and management of geographic, demographic, and socioeconomic information is required in order to be able to measure what is at risk. Regardless of the scale of the model, OpenQuake allows users to perform risk analysis with exposure models at any scale, as long as the model has the minimum required attributes. In addition to the number of elements in the exposure model, the modeler can consider replacement costs by differentiating the value of their components. For example, structural components, non-structural components, contents, and loss due to business interruption. You can consider different levels of occupancy, such as night, day, and transit occupants. It allows the analysis of insured portfolios with limits and deductibles, and even personalized information through labels. For example, it is possible to differentiate between elements exhibited in the same construction class depending on the socioeconomic stratum of the house or its built area. Now let's look at the last component necessary for loss and damage estimation. We will talk now about seismic vulnerability. Seismic vulnerability represents the likelihood of an element exposed to seismic hazard to suffer losses due to ground shaking. Similarly, seismic fragility represents the likelihood of an element exposed to seismic hazard to suffer damage due to ground shaking. In the language of OpenQuake, fragility is associated with damage as a result of the seismic event, while vulnerability is associated with economic or human losses. Let's start by taking a closer look at fragility. There is a correlation between the level of intensity of the ground movement and the level of damage suffered by an exposed element. We can see in the images that if there is no movement of the ground or lateral load, we should see no damage in the structure. If slight shaking of the ground occurs, it will produce visible damage, for example, in form of cracks in the structure. The greater the shaking, the greater the damage observed. The intensity can be so great that it causes permanent damage to the structural elements, or even the collapse of the structure. Although this process is continuous and occurs in a particular manner for each structure, risk modelers usually discretize it in a number of damage states. For example, slight, moderate, extensive, and complete damage or collapse. Damage states establish the level of damage that an exposed asset will experience as certain demand parameters are met. For example, inner story drift, peak floor acceleration, maximum displacement of the roof, and so on. The structure is considered in a specific state of damage when the ground shaking causes the limit established for an engineering demand parameter to be exceeded. For example, the capacity curve in this image indicates that if the structure exceeds its ultimate displacement, it would end up in the state of complete damage. In risk analysis, the fragility models establish the relationship between the probability of exceeding a number of damage states, such as slight, moderate, or collapse, given a certain level of ground shaking. This relationship can be described in OpenQuake using a continuous mathematical function, such as log normal functions, as shown in the figure. Here, we can see that the probability of damage increases with an increase in ground shaking intensity. The relationship can also be established by a discrete function, as shown in this figure. The structural attributes of a building, such as the construction material, construction system, height, and design regulations, have a direct influence on its fragility, making it more or less resistant to ground shaking. For example, these two curves correspond to two-story wooden structures, with the difference that the left represents a house without any earthquake-resistant design provisions, while the one on the right represents a house designed and built following a seismic design regulation. For a spectral acceleration of 0.6 g, we can see that the structure without seismic provisions has a 60% probability of exceeding light damage, as compared with a 25% probability that would be obtained for the properly designed structure. In fact, it has a much higher chance of exceeding any of the damage states. This is why, under the same level of seismic hazard, the most fragile structures present a higher level of seismic risk. The development of fragility models requires detailed analyses of the dynamic behavior of structures, and it is the objective of many research studies. In the OpenQuake platform, you can find multiple fragility models developed by different authors around the world. The models can be accessed, viewed, and downloaded in the OpenQuake format to perform risk analysis. The database also includes vulnerability and damage to loss models. Now we will address the concept of a vulnerability model. By definition, vulnerability models establish a relationship between the intensity of ground shaking and the percentage of loss of value or of affected occupants, such as a number of fatalities, given that this intensity level is reached. It can be seen in these two vulnerability models that on the x-axis, the greater the ground shaking intensity, the greater the fraction of loss of the structure. In OpenQuake, we have the option to specify vulnerability functions by means of the expected value of percentage of loss and its associated uncertainty. The uncertainty can be specified by means of continuous distribution, for example, log normal or beta distribution, or with a discrete probability mass distribution. There is also a correlation between damage to a structure and the value of the associated loss. To understand the level of economic or human loss that results from damage to structural, non-structural components and contents, we can use consequence or damage to loss models. Consequence models establish a relationship between the physical state of damage and the percentage of lost value or of occupants killed or injured. In this way, through the consequence model, the relationship described by a fragility model can become a vulnerability relationship. In OpenQuake, we have the option of specifying consequence models for each level of damage by means of the expected value of loss, as in the graph to the left, or with its corresponding continuous distribution, as on the graph on the right. Let's see with a simple example how we can combine the fragility and consequence models to derive a vulnerability function. Suppose we want to determine the seismic vulnerability of a portfolio of 100 buildings located at one point in our exposure model. These belong to a specific structural typology. Two-story wooden houses, whose seismic fragility is described by this fragility model. This model has 4 damage states: slight, moderate, extensive, and complete. To make this calculation simple, let's assume that the total value of buildings is $100. If these structures lose 10% of their value when suffering slight damage, 30% when suffering moderate damage, 60% when suffering extensive damage, and 100% in the case of complete damage, what would be the economic loss that would result from a seismic event with a PGA intensity, or peak ground acceleration, of 0.6 g at the location of the assets? According to our fragility model, with an acceleration of 0.6 g, 85% of the structures will suffer slight damage. However, not all of them will remain in this state. According to the moderate damage curve, 40% of the structures exceed slight damage and pass to moderate damage. From there, 10% of the structures achieved extensive damage and 4% reached complete damage. This bar graph helps us understand the final distribution of structures in each state of damage. In the end, we have 45% that are in slight damage, losing 10% of their value. 32% were in moderate damage, losing 30% of their value. 4% reached the state of extensive damage, losing 60% of its value. And 40% has complete damage, losing 100% of its value. As a result, we obtain the loss ratio of exposed elements, given that level of intensity, is approximated as 21%. In other words, this distribution of damage results in a total economic loss of $21. If we repeat this exercise for each possible intensity level, from an acceleration of 0g to 1, 2, or 3g, we would obtain the complete vulnerability curve of this building class, where we have a range of possible intensities on the x-axis and the loss ratio on the y-axis. At this point, we have already seen the 3 components necessary to estimate losses and damage: the definition of the ground motion, as we saw in the video about ground motion fields, the exposure, and the fragility or vulnerability functions. In the modeling of a seismic scenario in OpenQuake, we can obtain statistics on the distribution of damage if the damage scenario calculator is used, or economic losses if the scenario risk calculator is used. It is also possible to use the damage scenario risk calculator combining fragility and consequence models to have both damage and loss results. Here, we see examples of the results of seismic damage scenarios, such as the spatial distribution and number of buildings in each damage state, or the spatial distribution of economic losses for a hypothetical event near the city of Medellin. We observe that, as expected, the damage and losses are concentrated in the area nearest the epicenter of the rupture. In this way, we finalize the theoretical framework on seismic risk for a scenario. With this knowledge, we can proceed to carry out a practical exercise in which we will calculate the damages and losses for a seismic scenario using OpenQuake.